Hi everyone. In this section of the course we will discuss higher order derivatives. If differentiating once was fun enough, then why not do it 2 times or 3 times? So far we've insisted on the distinction between the meaning of f at a, which represents the y component of the curve when x is a, and f prime at a, which corresponds to the slope of the function, or if you prefer, the slope of the tangent line to the function at coordinate a, f of a. So on the one hand, we have a point's height in the Cartesian plane, and on the other hand, we have the function's inclination as it goes through this point. Now we will add to the mix information that is provided by calculating the second order derivative, which we denote as f prime prime at a. This will correspond to the concavity of the function y equals f of x at coordinate point a, f of a. More specifically, if the second order derivative at a is positive, then the function is concave up at this coordinate point f of a, f of a. You can visualize a curve that is concave up if it has a smiling shape. So the tangent line to the curve at point a, f of a would then lie below the curve. If the second order derivative is negative at point a, then the function will be deemed to be concave down at the coordinate point. We can visualize a curve that is concave down when it has a frowning shape. The tangent line to the curve at a, f of a would then lie above the curve. Finally, if the second order derivative at a is 0, then the function is neither concave up nor concave down at this point. Usually means that the function has turned into or has a linear aspect through the point a, f at a. So it's not curving up or down, at least momentarily, through this point. Graphically, here's an example of a function for which f at a is positive. This is the case because you notice the y component at the point a that's indicated is above the x-axis, so it has a positive y value. The derivative of f at a is positive as well, as denoted by the slope of the tangent line, which is certainly positive. However, the function is concave down at point a. Its second order derivative is negative, and you can detect this by the fact that the function has a frowning shape as it passes through the point that is highlighted. Or, if you prefer, the tangent line remains above the curve at this point. Here's a point where f at a is still positive, as the y value is greater than 0. The slope of the function, so the derivative at a, is 0. And the function's second order derivative is still negative, which means the function is concave down. Again, you still have the frowning shape through the point, and the tangent line has remained above the curve itself. Here's an interesting point where now f at a is negative. The y value of the coordinate point that's indicated is negative. The derivative is negative as well, since the slope of the tangent line is negative. So this is a point where the function is decreasing. And the second order derivative is 0. As you can see, the function has taken a linear aspect, at least for a brief moment, in the region around x equals 2 in this case, or at point a that's indicated. The tangent line is neither above or below the curve, it's actually going through it. Finally, here we have a point where f at a is 0, so its next intercept. The function's slope is positive, so the derivative is positive. And the second order derivative is positive. The function is concave up, as it has a somewhat smiling shape. The tangent line, therefore, stays under the curve in a region where the function is concave up. From a purely technical point of view, calculating a second order derivative simply means differentiating the result of the first order derivative. In other words, to find f prime prime at x, you would simply use the derivative f prime of x and differentiate once again on the result of it. We can use either Newton's form or Leibniz form to represent these operations. Here's an example where f of x is defined as x cubed minus 6x plus 5. So this is a third degree polynomial. We're going to compute and interpret the value of f prime, and f prime prime at x equals 1. So firstly, f of x is x cubed minus 6x plus 5, which means that calculated at 1, we will actually get a result of 0. I'll let you think for a moment of what this means graphically. F prime of x is obtained from f of x by using the power rule on the different terms that have powers of x. We're also using the subtraction and addition rule. 3x squared minus 6 is the outcome of the derivative, and f prime calculated at 1 is minus 3. Again, I'll let you reflect on what it means for f prime at 1 to be minus 3. Finally, f prime prime of x is obtained from the first derivative by differentiating once more. 6x is the outcome of the second order derivative, and calculated at 1, f prime prime's value is 6. So, looking at these results, here is how we should be interpreting what has happened. The first number we calculated was f at 1, which is equal to 0. Graphically, this means that when x is 1, y is 0. We essentially have an x-intercept. F prime at 1 is equal to minus 3, which means that the function's tangent line has a slope of minus 3 as it passes through coordinate point 1, 0. Finally, the second order derivative calculated at 1 is 6, which means the function is concave up. In the graph that is presented, you can actually tell the function is concave up by its smiling nature as it passes through point 1, 0, or by the fact that the tangent line is remaining below the curve at this point.